Hello everyone, I'm Pouya from BSC Memory Systems Team, and I'm going to present you the mess of memory today. The idea is that I'm presenting you the paper that was done in the collaboration of 3 teams in BSC and Micron Technology. As you see, this paper has huge list of authors, and each of these authors will have their own story about this paper. Today I'm going to tell you my story. This paper was published in Micro 2 years ago, and since then we went all around the world and presented. Why the flags look like this here? Okay. We presented in all around the world. We present this first initially in US. We won Best Paper Runner-Up Award in Micro. For people who are not from computer architecture, this is the top conference in our field. And then we went to another conference in US. We won the most controversial truth-telling panel discussion for this paper. Later, we were invited to EPFL University in Switzerland. We go there and we present the paper there. Later, we were invited by Micron Technology to Italy. We went to a memory workshop and we present the paper again there. And then last year, we went to Korea and we present this paper in a tutorial, also in another memory modeling workshop. And after visiting 3 different continents, we are coming back to home to Spain, Barcelona, to present this again here. But what is this paper about? This paper is trying to answer one core question. So far, what is happening is that we have bunch of benchmarks that they are trying to evaluate the performance of main memory. They are called like Stream, LMbench, HBCG. We also have some memory models and simulators, such as DRAM Sim Ramulator, that they are used to model the performance of main memory. And we also have some memory-related application profiling tools that with them you can understand whether your application is memory-bound or not, such as CPI stack or roofline that you already know from the last discussion. The core of this study is that is there any unified view that can that all these 3 different aspects of memory system are combined with through that? Somehow, is it anything that can bind these 3 different separated islands together? And this study is trying to address this. And to address that, we need to understand what is main memory performance. From Computer Architecture 101, what we learned is that memory performance can be considered a fixed latency or like an empty road, which means that whenever you have a request to a main memory, it will take you a fixed amount of cycles, fixed amount of time to go to the main memory, get your data, and come back. And as you increase the pressure on main memory, what is happening is that your latency starts to increase because you will have some contention. So this time when you go to memory and come back, you might switch some line, and that would take you more time to come back. And as we start to increase the traffic on the main memory, what is happening is that the time that takes you to bring your data starts to increase until the point that you will have a heavy traffic, you will saturate, and the amount of time that took you to bring your data or reach your destination would be increased significantly. So our first step was that, okay, if this is going to be the performance of main memory, let's create a benchmark to generate this from actual hardware. So what we did is we started to generate a benchmark that is going to generate this bandwidth latency curve. And how he does it is through the use of 2 micro benchmarks. The first one is the traffic generator. And the idea of this traffic generator is the same as a road that you have a bunch of cars. It will generate memory access, reads and writes. And then, based on some configuration, you can have a lot of traffic or a small amount of traffic. And based on that, you will be on the different part of the curve. And then the next idea is that, as Alexandre was explaining, there are some hardware counters that they are able to measure some stuff about your hardware. One of these hardware counters or on-core counters that you can use to measure the bandwidth of the main memory. So with that, when we are running our traffic generator, we are able to measure the memory bandwidth that our current benchmark is generating. Then, on core 0, we run another benchmark, that is pointer chase. And the thing that the pointer chase is doing is that it tries to measure the latency of memory access. And with this, we will have the y point of each of the dots. And having these 2 points, x and y, we will have 1 point, and then we start to run our traffic generator with another configuration with higher traffic, and we go to the right side of the curves. And with lower traffic, we go to the left side of the curves. And then we connect all the points. We will have these bandwidth latency curves that represent the memory system performance, which is this one. And then the idea is that how we can generate this. This is a bit like more, maybe this part is a bit for computer architects. So if the rest of people in the audience did not understand, it's okay. This is not very important to know for the rest of the discussion. How we generate this traffic is through a very simple couple of lines of assembly. And essentially, it is lines of load and stores that send memory requests to main memory. And these memory requests are independent of each other. So through the out-of-order execution and memory level parallelism, CPU will be able to generate all of them very close together. And then between these memory instructions, we will have some knob function, and the job of this knob function is to pause. So put some pause or a sleeping between these memory accesses. So with this, we will control the intensity of memory operations. And then when we run this on all the cores except core 0, that is for pointer chase, what will happen is that we are going to generate this traffic. Then on core 0, how our pointer chase is working. The way that the pointer chase works is that it has the same thing, similar to this in terms of it has a bunch of load instructions, with one exception, is that then each load is dependent on the result of the previous load. So when you are starting to execute this benchmark, what is happening is that if you execute 100 load instruction, it exactly takes 100 times going to main memory, getting your data, and coming back. So if you divide your number of times, your execution time to number of times you go and come back, you essentially have your access latency. And then when you combine these two benchmarks together, what will happen, and you run it concurrently, you will have the latency for each specific load. Okay. Then what will happen is that we implemented this benchmark, and we start to run it on the hardware. And what we saw is that we will not have one bandwidth latency curve, but we will have a family of bandwidth latency curves. That each curve corresponds to one read to write ratio, because what will happen in your main memory is that you can submit all reads, or you can have reads and writes together. And based on whether you are 100% read, or you are half read, half write, or you are 100% write, you will be on different curves. So as you see, for all of them, the latency starts to be fixed, and slowly it starts to saturate until it reaches huge. In addition to the result of this mess that is curves, we also always in our benchmarking show the position of a result of the stream benchmark in our results, since stream benchmark is the de facto memory benchmark that everybody uses. So for us, we wanted to make sure that the user has some feeling what he gets in addition to the stream result. Okay, what we did after we developed this benchmark is that we deployed it on a vast majority of server CPUs, from different generation of Intel CPUs to different generation of like Amazon, AMD, Power, to see how different memory technology works. What we saw is that even same manufacturer, same memory technology, there are some differences in memory system performance. And if we pick two different CPU manufacturers that use the same memory technology, what we observe is that the memory system performance and the bandwidth latency curves can vary a lot. Later in the future, Victor and Mariana are going to show you how this will impact the application performance. Okay. And what we see also is that the difference from like CPU in terms of latency and bandwidth to high-end GPUs like H100, NVIDIA that we had in Mare Nostrum 5. For those guys who work on AI and who cares about main memory a lot, bandwidth and these things, talk to Xavi. Xavi took this memory benchmarking of GPU to the next level, and he had so many interesting things to show and discuss. He has some information about reaching some bandwidth like 4 terabytes per second for some high-end GPUs. So, but for that, you need to talk to Xavi. Okay. The result that I show you guys so far is the result we got from for the MES paper. But after the publication of MES paper 2024, we were continuing our exploration. One of the systems that, thanks to Intel, we get the access and we could evaluate was these new high-end Intel servers with this new memory technology that called MRDIMMs. These MRDIMMs are, one of the good things is a new memory technology, and one of the very amazing things about this technology is that when you buy a server, usually if you want to have a better memory technology, what you need to do is buying the whole server again. But with MRDIMMs, you don't need to buy a new server again. You can just take out your current DIMMs that you have, and you just replace it with MRDIMMs in the same slot. And what will happen as a result of that, you can get higher bandwidth, which means better performance sometimes, and or you can get higher capacity, and there are a lot of design choice that previously it was not available, and this is available because of this technology. And thanks to Pouya running this on Intel server, we have the bandwidth latency curve for this server, and as we can see, it has a huge amount of bandwidth, and here we have the analysis of that, which means that it gets around 2.5 times more bandwidth than Mare Nostrum 5 that we currently have, just having a better memory technology. And also, what is very interesting is that in terms of unloaded latency, the latency is the same as normal Intel server, which means that there was no cost in terms of latency adding to our system. That was very interesting also to see that in terms of efficiently using bandwidth, which means that the maximum bandwidth you reach versus the theoretical bandwidth, it was very similar to normal DIMMs that we used to use, which means that there is no downside, I would say, to this technology, or at least not in terms of performance. And then the next technology that is also very interesting, characterization was done by Mariana. So for each of these, I'm telling the names, so if you want to know more information, you know who you need to talk to. And what is interesting about this CXL memory expander technology is that these things are like new slots that goes inside the PCIe port. So it's not going to replace your main memory. What will happen is that it will add performance to your main memory. And what is happening is that these things add performance and capacity to you, and we get access to this thanks to Micron technology program. And as you see, we have the bandwidth latency curve for this CZ120 device of Micron technology. And as you see, in terms of bandwidth, it can provide you like 30% more bandwidth than you currently have in your server. This is also very good because this is also plug and play in terms of you can add it to your server without changing your server. Or if you don't need it, like you can take it out, which is very beneficial. Also, it adds capacity, and in terms of latency, it is higher than local latency, but it is comparable and very similar to accessing your remote socket in the same node, which is very tolerable, I would say, in terms of performance. And then the last one is that we have access thanks to ourselves, BSC, that is NVIDIA Grass CPU that we have. And this new technology is very interesting because it is using this LPDDR5 memory technology. This one is very interesting because this is the first time that any HPC CPU use this memory technology. This memory technology usually used in your laptops or in your cell phones, but not in HPC. And now we are going to see the result of what is happening if you use this in the HPC. Okay, here is the bandwidth latency curve. what we see is that in terms of bandwidth, they can reach a very quite high bandwidth compared to Amazon Graviton 3 or Mare Nostrum 5 that we have. They are reaching like 75% more bandwidth, which is like very good. And I don't know, this was Pau or Victor getting it? Pau. So if you want to talk more about GRAS bandwidth latency curve, talk to Pau. Then, something that is we should be careful is that in terms of latency, this is latency is higher compared to Intel platform, which means that if your application probably is latency sensitive, maybe you don't want to use NVIDIA GRAS. But I mean, this is something that the guys will explain you later what latency means, what bandwidth means. But this was also another system. But for me, it was very interesting, especially this part, that we can reach such a high bandwidth with such a efficient, low power DDR memory that usually used in your cell phones. Okay, now, so far, whatever we see is that profiling actual hardware, similar to generating the roofs in the roofline model. Now, the idea is that, okay, can we use this information about the hardware and understand what is happening when we run some application, whether it is memory bound or not, or at least how it uses the main memory. So what we do is we show here how we can profile an application and do this analysis. To do that, first we need to understand how the tracing works, because we need to do tracing. And the idea of this tracing is that you have an application such as HPCG that you are running on your Mare Nostrum, and then at some time spots, what you do is you start to capture some information from hardware counters. For example, here we are working on main memory, so we are interested in reads and writes. So what we do is, here we show, for example, at T0, what will happen is that we start to dump some stats in a text file that's called trace file. So what is happening at T0 is that we get one line, 2 lines of information, and in each line we have one entry that is the time that we did this measurement. The second entry, the next entry, it would be the name of the thing that we are measured, like the name of the counter. For example, here in the first line, we are measuring number of reads, and in the second line, we are measuring number of writes. And then the middle one is the counter value, which means the number of reads that we have and number of writes we have. Because if we have number of reads and writes, and we have the amount of time it took, we can calculate bandwidth, and this would be actual bandwidth measured on the memory bus, which is the physical one. And the idea is that if we start to continue execution and capturing the information, at each time spot, we start to capture 2 more lines, and then we will have the whole trace file for all the application execution. Then what we can do with this trace file? What we can do is we can get this information from the application based on that how much was the used bandwidth and the read to write ratio of the application, and we can print it on the bandwidth latency curve, very similar to printing the information of application in the roofline. And what will happen is that we are showing that in the black line are the bandwidth latency curve of Mare Nostrum 4. And what happens is that each point is 10 milliseconds of HPCG running on Mare Nostrum 4. And what is happening is that here you can see that how HPCG is using memory. Sometimes it is in the high bandwidth, sometimes all over the place it is in a low bandwidth position. But as we see, the majority of the density of the application is in the high bandwidth place. Again, how this performance impacts when you change your memory system, it will be explained by Mariana and Victor in a very detailed mode. Now, I think we are done, and now Victor will explain you how this can be actually done in terms of profiling.
Okay, hello everyone. So, we've devised the steps we need to follow to achieve these dots you saw in the chart with these 3 simple steps. The first one would be getting the memory curves, same as Pouya showed just now. And to do so, we're also adding the sources for you to do it. We have a benchmark available on GitHub that you can ideally run in any system. If there's any system you find that cannot run it, please let us know and we'll try to adapt it. And you can achieve the curves from there. That will generate the raw output files. This is one part of the equation we need. The next step would be to profile your app. To do that, again, you can choose the tool that you want. But we currently use the hardware counter approach, so we need a tool like Papi, Perf, Xirau, Liquid, whichever your counting profiling tool is preferred. For this demo, we'll be using Perf, as it is the simplest to use and to parse the output of. And finally, once we have the trace, as Pouya mentioned, with all the individual time samples, and you have your curves on which to plot your data, the next step would be to then visualize them. For that to that end, we've created two sample traces, one benchmarking stream, which is a very bandwidth-intensive application, and the other benchmarking Google Multi-Chase, which is a more latency-bound application, essentially very similar to what Pouya was mentioning about how we measure the latency for each of the dots in the curve. In the case of Multi-Chase, those are all dependent loads, so it will always or mostly all the time go to main memory if it's done right. So we'll also see those two different scenarios. I'll also be showing different examples of curves, so we're going to be going over the different curves we have in our in-house system of Mare Nostrum 5. Starting from the regular GPP node, we'll also show how there's a slight difference between the GPP node and the high-capacity GPP node. This was brought up to us by John McAlpin, who's here in the room, and we appreciate very much. And you'll see how just by changing the capacity due to how the DIMM itself is manufactured, we get a slight increase in peak bandwidth, around 20% increase. Then we'll cover also the HBM node, the Grace node that Pouya showed, and we'll also show the latest GPU curves for the accelerated nodes GPUs, which were obtained by Javi, as Pouya mentioned as well. So before we show the demo itself, we have this QR code and this link, because the idea is that on the website I'll show now, we have uploaded all of the traces and raw data used for this demo. So you can access the actual JSON files where we store the curves. You can access the trace files we're using for stream and multi-chase. So you can visualize yourselves everything I'm going to show here. So let me see. So on the website, you'll find the resources page. This has also been mentioned in some of the previous slides. We have all of the references and papers and slides uploaded. And if you go to the visualizers part, you'll see how we currently have these three visualizers. We'll go to the profit and top-down ones as we get through the day. But we'll start with the MES one. Ideally, this should be your operating system, but it is available natively for all the others in case you have different ones. And if we scroll a bit below, we have all of the traces that I'm going to be showing and using. So you can either check it out as I go, or you can do it at home or whenever, or not doing it all, whatever you prefer. You'll find the traces for the regular GPP node, the high memory one, and then the sample curves I'm going to be showing. Okay, so let's see where the demo is. So once you download the MES visualizer, so what you'd find up here, and you open it, you'll be greeted with this view here. What we're seeing in this UI is, by default, Mare Nostrum 5 GPP node regular memory is plotted, and these are the curves we're seeing here. And you'll see that we have the list of curves we're going to have loaded. As of now, we only have one, but we'll keep loading more as we show the different examples. And we'll have also the option to load multiple apps, which we'll see here, and we can then click dots on those apps to visualize them here. To generate new traces, other than the ones we provide, we also give you this snippet here, which is essentially the most basic version of the perf command we used to generate these traces. You can just copy it here, change the application and the output file name, and generate it yourselves to also visualize it in this tool. So the files you'll see look like this. We have multiple CSV files, which are the output format or the preferred output format for perf, so that we can plot them in the tool. And we have multiple JSON files to view the different curves. Let's start seeing the two example apps I mentioned, so Stream and Google Multi-Chase, on the current curves we have plotted, which are, again, the Mare Nostrum 5 general purpose partition default memory curves. Let's start by plotting Stream Triad, for example. The specifics of the benchmark were already covered by Alexandre a few minutes ago, where he mentioned how this is doing some flops and then some operations. And the objective of benchmark like Stream is to try and achieve peak bandwidth, right? So get as close as possible to the maximum sustained bandwidth. And we can see how whenever we plot stream on these regular Mare Nostrum 5 GPP node, we see most of the dots lie at the end of the curve. One question you might ask is, how do I know these are most of the dots? We added the option to tune the opacity of each dot, so we can lower it so that each individual dot would be less transparent. And what actually will happen if we lower this slider is that most of the dots that are around the other points of the curve, like the ones we see down here or some of the ones up there, start to fade away. But we still see this cluster of dots very prominently, right? We still see the red really bright. That essentially means we have many dots overlaid on top of each other, so most of the samples throughout the execution of the code are there. If I now open the other stream kernel, for example, let's see copy. We'll see how it is also at the end of the curve, but it falls on a different curve, right? As Pouya mentioned, each of the individual curves covers a different read to write ratio. So these two different kernels within the stream benchmark have also intrinsically in their code different access ratios to memory. They access different read to write patterns. That's why we see most of the dots for copy mapped on this curve here, and most of the dots on triad mapped to these other curves here. And again, if you try this tool yourselves, you can then click on the dots and see information about the specific bandwidth and latency that specific dot perceived. Okay, this is what we see for bandwidth-intensive apps like Stream. Let me unload these apps from the visualizer now so we don't get confused with the rest. And let's see what happens if I load Google Multichase onto this same view. What we see is that opposite to what we saw with Stream, where most of the dots were to the right, when we load Multichase, we see most of the dots profiled at the start of the curve. And again, if we lower the opacity to check how many dots are there, you can see how most of the application is overlaid on those two regions at the start, right? And we talked about memory performance and how can I understand what should I do to improve my application and what can I do given my memory system. We saw these two examples where we had streams to the right of the curves and pointer chase to the left. So these two scenarios are quite different in terms of what we should do or what we could do to try and get better performance. If we were to increase peak bandwidth and make the curves bigger, like the different curves that Pouya showed, we could guess, we'll see later, but we could guess that Stream might benefit from that. Actually, Alexandre already showed that when we profiled Stream on HBM, we saw how the roofs grew, so it became higher. I remember it was 4 times higher, right? And Stream also grew in performance, and we also saw it 4 times higher. So we probably would see the same thing with the curves. Where we won't see the same thing is with this other region here, with Multichase, where no matter how much bandwidth I give you, this will remain mostly the same, right? Because it is not influenced by bandwidth. It is still memory bound because you're having to access main memory due to the nature of the benchmark, and you will still have some delays because you're accessing main memory, but changing the curves to curves that have just higher bandwidth will probably not give you any performance gains at all. Let's see how that looks on different curves. So if we load, where is this? For example, let's load the high capacity curves, the ones I mentioned that are the same CPU, just we get slightly higher performance. We see now that we have these green curves here, which are slightly more to the right. You can also see how the lead-off latency is the same, right? Again, just by guessing, we would probably assume that Stream benefits from going over to these curves. Multichase doesn't, but we won't be guessing. We'll see what happens exactly. One important thing is that by how the nature of the visualizer, you can technically just change where the application is plotted for the other curve, but this would not be accurate for the system. That would not be a correct thing to do because these dots that we're seeing now were measured and ran on the regular memory node. So just changing nodes doesn't magically give you the result of what it would look like to be running them on the other memory system. For that, we have the mention here. We will be covering that on the later presentation with Profit. But we actually have the traces we obtained on that other high capacity memory. And we can move the same copy benchmark. And in this case, we do need to choose it so it is correctly plotted onto the high memory one. And we can see how, indeed, this one was achieving 187, gigabytes of bandwidth, and when we ran it on the high memory node, we saw 223 gigabytes per second, right? So we saw this performance increase. But again, just for redundancy, but if we load multi-chase on this high memory, it's virtually the same, right? They overlap, and I can actually hide, so this one here, the regular one, and we'll see that they're mostly the same thing, and they are mapped on the same place. So we can also move the same approach and the same analysis and the same methodology we're using, where we're plotting dots on curves, to any other set of curves we want to, right? So we mentioned we have some other examples for you. We loaded the HBM curves that Alexandre showed the roofs for. This is how they would look like, and we could plot applications on these ones too. We also have the curves for Grace, which again is this system where we have slightly higher latency, but we get also significantly good bandwidth. Let me show at the same time as well the curves for Maranastrum 5, so you can see the comparison between each, right? So we can see the different latency levels. When we talk about unloaded latency, this starting point is the minimum latency you could ever perceive when you're accessing memory, right? And as Pouya mentioned, the more bandwidth we generate, the more the significant increase we see in latency when we do that. And we see how further away they get in terms of bandwidth, depending on the memory technology. These examples are quite different to what we would see if we then move to GPUs, which have significantly higher bandwidth. So if I were to drag a GPU curve over here, we see how it dwarfs in comparison all the other memory systems. But also this is a completely different system. And in the case of GPUs, we also brought an example for you to see, which again, same methodology. We're sampling in time the application, measuring the actual performance counters that are doing the operations. And we can visualize applications on these curves. In this case, we're plotting a gem, a matrix multiplication, onto the GPU curves. So this is what we get from the visualizer side. So again, you can generate your own traces or run our benchmark and generate your own curves and visualize them yourselves. But let me see. Okay. So if you already start to see how simple it is, so there are quite a few previous steps, so getting the curves or running your app, but it is quite fast to get there, and you already start to see visually how your application is behaving. If you already start to see this and start to get this feeling of, okay, I kind of get it, we consider this as already a success from our side. And the idea is that, again, you can apply the same hammer to a different layer, so you can use the same principles with different memory system configurations like DDR5 and HBM, CXL expanders. We also did this in the past, as was mentioned in previous slides, for Optane or others, as well as new technologies like the unified bus that was introduced by Huawei. And similar to CARM, this is also available in Paraver. So if we combine this with Xirau and Paraver, Xirau for the counter reading and Paraver for the visualizing of the output trace, we can see very similar plots in terms of the visualizer we had, right? So we have the dots sampled in time on top of the curve, but we complement this information with everything that Paraver can bring. In this example, we're seeing how we have the trace in time. In this case, we're mapping the actual value of the stress score, so how much to the right and to the high end of the latency you are in. And we can see how different regions of the app map to this stress score. So to see exact MPI calls or MPI regions or whatever things you want to map onto the Paraver trace, map directly to how the curves visualize. We also have the histograms here, so you can see how in this example, most of the application falls within a 20 to 30% stress score, so it isn't too stressed in general, but we have some percentages in the higher ends, so which are saturating more memory or adding more pressure onto memory. So hopefully you've seen how easy it is to visually see how your application is performing in these memory systems. And when combined with Xirau and Paraver, of course, you can get even more insights than what we just provide with the counter sampling and the curves. For details on how to get started, you have the guides on our own website, and you also have the repository for the MES Paraver integration, together with the tools page. And you will also see a practical example of this on the MES paper that was published in Micro. And for any other doubts you might have, the BSC tools team has a lot of training material, like the one they did last week, the workshop you see up there to the right. And if you're interested in this work, please contact them or us if you have any MES-related questions on that. We also added to the end of the slides, for your interest, tons of different links and resources you can check. You have resources to the benchmark, to the MES Prever site, to the website itself, where we also go into more detail into how MES works. You have our contacts, so you can ask us the individual questions related to GPUs, to profit, which will be introduced by Mari, benchmarking, whatever you need. And then some suggested reading materials that we think might be beneficial to get better understanding on what is going on behind the scenes with all of these different curves. And that's it. Thank you very much.
Thanks, Victor. Thanks, Pouya. So, two things. No, I'm here. So two things before we move to the next presentation is one, during the intro, I told you guys, you're not helpless. This is not constant for decades. I mean, you have seen so many curves, you have seen so many options. There are many things you can do today. I mean, if you can do today in Mare Nostrum, right? So get this bad idea out of your head that there is nothing to do about it. Okay, so that's number one. I hope that you start to feel it. Okay, number two, and something completely different. Please sign the attendance sheet. I will pass this through the room. In case that your name is in the list, find it, just sign. In case that your name is not in the list, just add it. Right? So we have some space at the back to do it. We need it to justify the expenses for the course. Thanks a lot.